lesson is about the central limit theorem, and it is very closely related to what we've done previously with the normal distribution or standard normal distribution. So the theorem itself, first of all, I know that when we read math theorems, they can be fairly wordy. So some key things to look at is that you've got sample sizes of size n, and n needs to be greater than 30. So make a note of that. N needs to be greater than 30 for the central limit theorem to apply. And then what happens when n is greater than 30? The sampling distribution of x bar. Pause. What's x bar? X bar was the mean of the sample. So that means it's the distribution of sample means. Can be approximated by normal distribution. And that normal distribution would have a mean mu and a standard deviation of sigma over the square root of n. So the fact that we're going to say when we can approximate with a normal distribution, mean is mu, but standard deviation gets adjusted. It's no longer just sigma. It's sigma over the square root of n. Now, you will be asked what this is actually meaning, and I've got a lot of it here for you at the bottom then. If you were just going to kind of rephrase that, you can take a population that starts with any distribution, and the distribution of the sample means will approach normal as the sample size increases. So we're not saying the original population ever becomes normal or that a sample is normal, but the sample means when you're taking x bar. So we're not going to go great detail into that. You're not going to have to do it, but it'd be like if I took a sample of 30 men and took their heights and found that mean. And then I took another sample of 30 men and found the mean. And then I did it again. And then I found out what the mean of all those sample means is. Well, it could be a pretty good estimation of the population, but it wouldn't be as good as if my sample size had been 50 or if my sample size had been 100. So it gets better as our sample size increases. And we're talking about the sample means. Okay, now as we apply this, these are then the formulas that really apply to it. You're not going to have to stress too much about this mu. The little subscript here with x bar just means that this is dealing from the sample means. So the population mean from the sample means will be the same as the population mean. The big deal for you as a student is probably to recognize you don't need to change it, okay? The mean from one is the mean from the other. Now, the standard deviation of all the values of x bar does need an adjustment. We're not going to say sigma of x bar is the same as sigma. You have to take that and divide it by the square root of n, and it'll be important that you can do that. On another slide, I have this formula again, and you can kind of copy it down there if you don't have it right now. It might be worth noting that that sigma sub x bar is called the standard error of the mean, and it can have its own abbreviation. So if you ever run across something that asks you for the standard error of the mean, just know that you get to use that exact same formula. The z-score conversion is slightly different also. When we have regular data, then we have an x value and we subtract the mean of that group, which was x bar. But here our x bar has become our data, and we are going to subtract the mean of the population. We also have to do that adjustment again. Instead of just putting it over sigma, it's over the new standard deviation for the x bars, which is sigma divided by the square root of n. Now, you're not going to have to use this formula a lot here, but this one with the little sigma adjustment, you have to use, and you have to know that the means are the same, even with your calculator. The slideshow that I've got for you here is so much shorter than the Pearson one because I'm expecting you to be able to use your technology. Whenever you're going to do a problem, then these are application problems in this section, you need to, as always, read carefully. But some keywords you're looking for this time. You need it to tell you that the population has a normal distribution, because that's one way you know you can use your normal CDF or inverse normal. And the other thing that you can look for is that the sample size is greater than 30. And that's an or case. So if you don't have a normal distribution, or you don't know that the distribution is normal, or even if you know it's skewed, if your sample size is greater than 30, you can still use your normal CDF and inverse normal. So look closely for those words, and if neither one of those things happens, then you cannot use this. Okay? The next thing you'll need to calculate is, are you finding an individual value or the mean from a sample? Now, the formulas that are here are important, but the key thing from it has to do with sigma. Okay, that's going to be your most important thing. If you're dealing with an individual, you use sigma for your standard deviation. However, if it's from a sample, it is sigma divided by the square root of n, and you have to make that adjustment. So the standard deviation, if you're getting the mean from a sample, is sigma divided by the square root of n. All right, let's look at how this can apply. An elevator has a placard stating the maximum capacity is 4,000 pounds or 27 passengers. Well, if you take 4,000 pounds and you divide it by 27 passengers, then the mean passenger weight is 148 pounds when the elevator's full. Okay, assume the elevator is filled with 27 adult males. And the males have weights that are normally distributed, okay? That was one of my key words, right? You either have to have more than 30, and here we only had 27, or you have to know it's a normal distribution. Now, on this normal distribution, the mean is 189, and the standard deviation is 39. Find the probability that one randomly selected adult male has a weight of greater than 48. Remember, if you only have one individual, and I'm going to back up to this previous slide, if you have an individual, you are simply going to use sigma for your standard deviation. You don't have to do anything to it. So what you see right here is that the numbers I've put in really come from this mean of 198, where this is my mu, and the standard deviation of 39, where that's my sigma. All right, I still used a lower since I wanted it to be greater than 148. I've got a lower at 148, and I put in extreme upper. Here it's all nines, but you know, you can do the 1 times 10 to the 99 also. And so I think you know where to get to this normal CDF now. And so we just took all that and we pasted it, and we get this 0.8534 approximately. And so that would be the answer to my question, that it's approximately 0.8534, a little bit more than 85% probability. All right, now this is part A. That's because this original question, when it comes up, there's actually 2 parts to it. I just needed you to be able to see the calculator readout rather than type it all in. That saves a little time now that you know how to get there. So let's look at this next one. Same setup at the beginning, still normally distributed, and we still have this original information that the mean was 189 and the standard deviation is 39. However, in the problem this time, we're not dealing with one individual. We have a sample of 27 males, and we're looking at a mean weight greater than 148. So previously we looked at the chances of one individual being greater than 48, but here it is the sample means. So when you are dealing with the sample means, you have to adjust sigma. So instead of using 39, you have to figure out what 39 divided by the square root of 27 is. And again, the 27 came from the 27 adult males, which is n. All right, so the adjustment has to be made on your n because you're actually going to use the same place in your calculator to find it. The only thing different here is that adjustment for sigma is 7.51. So then when you work that out, you get this 0.99999 blah, 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 blah. And that means it's almost certain. So occasionally also you'll be asked to interpret or choose the best interpretation. So kind of putting this together, there's about an 85% probability that an individual male will weigh more than 148 pounds. And there is an almost certain probability, because you know 1 would be certain, so this one's really close, almost certain probability that 27 randomly selected males will have a mean weight of more than 148. But if their mean is more than 148, then that means the overall weight is going to be more than 4,000. So given the safe capacity of that elevator was 4,000 pounds, it's almost certain that the elevator is overweight if it's filled with 27 randomly selected adult males. That would be the interpretation. And this is really how you're going to go about the problem. So one last thing before I go on to the next, just you've really got to read closely and make sure that you know whether or not you need sigma divided by the square root of n when you've got a mean, or whether or not you are going to use sigma directly from the problem. Do you need to make that adjustment? Okay, this last slide has a bit of a clip from a homework problem, and it's really, this problem had parts A through C, and I think this is the picture here is coming from part B, but we'll take you through it. If females have pulse rates that are normally distributed with a mean of 72 beats per minute and a standard deviation of 12.5 beats per minute, complete parts A through C below. Now I kind of added this sentence back on here. It did in part A, it told us that a female had a pulse rate of 78 beats per minute and asked us to calculate what the z-score was. Okay, and I believe to do that, since I needed a z-score, I may have just used the direct formula. And I say that the direct formula was given right up here, x bar minus mu divided by the standard deviation over the square root of n. I don't have all the information on here because I calculated this from part A, but it told us what the sample size was. And anyway, I calculated then that z-score was 0.48. 0.48 for a z-score. That's really not the point that I'm trying to make right now. It's just that once you have that z-score, with this information, there's more than one way to do it. If you have a z-score, then a z-score goes with a normal CDF that has a mu of 0 and a sigma of 1. So if you're using a z-score, you want to have mu at 0 and sigma at 1. Okay? And we were trying to find an area to the left, so that's why my lower is extreme. On the other hand, if you don't use the z-score, then you can get the same information by just changing your mu and your sigma to what is given in the problem. That just kind of depends on whether or not you've got a z-score or you don't have a z-score. If you have a z goes with standard normal and standard goes with 0 and 1. If you don't have a z-score, you're not going to use the z-score, then use the mu and sigma within the problem. Now, when do you adjust sigma? When you're not dealing with an individual. Here, this was a female, and so I didn't make any adjustment of sigma. Now, what this screen here is showing then is that for the first one, I did the 0.48 and 0 and 1, which means I was using the standard normal. On the second one, I used the numbers for the individual as given in the problem, and both of them give the exact same result. So either way, the area in this particular one, if you were needing to write that answer, round to 4 decimal places as needed, it's 0.6844. So some of the problems, you have a choice of whether or not to use it as a standard normal or just a normal, and you can get the correct answer either way. Cannot stress it enough though. Standard normal has sigma and mu. We've got mu sigma 0, 1. If it's not standard, then you need to use the actual values. The time you need to make the adjustment for sigma is if you're dealing with the mean from a sample, and then you need to make the adjustment for sigma to be the standard deviation divided by the square root of n. All right, well, that's the end of our slides. I hope that helps you out. Send me an Ask the Instructor question or an email if you have any more questions.